Today we begin with an alternative method to derive equations of motion of integrable many-body systems, which was suggested by Krichyver, and I will show this method on the simplest example, on the example of Calogero-Moser model. We start with a linear equation for wave function psi, which is the first auxiliary linear problem for Kp hierarchy. U is a function, and the idea is to investigate when this psi function as a function of spectral parameter, which lives on complex plane. When this equation has meromorphic solutions. Meromorphic, so here Z is a complex number and coordinate x is also extended to complex plane, and we are interested in a solution to this equation which has a pole in x at some point a. So psi. In fact, here we even don't need the dependence on spectral parameter. This equation in general has a family of solutions parameterized by a spectral parameter, but here we don't interested in it. We are going to find just one solution to this equation as a function of x. So suppose that at some point a there is a singularity. What type of singularity this could be? Simple substitution to this equation of different possible poles leads to a conclusion that this pole must be of the second order with constant coefficient which can be put equal to 1 and sign minus in front of this pole, plus less singular terms and regular terms. And also the constant, the first order pole is absent here, and the expansion is u0 plus u1 times x minus a, and so regular part of this function. And the question is, and this pool can depend on T. And we are going to answer the following question. What are conditions to these functions and the pool A as a function of time such that this function is meromorphic? Because in general, it may have singularities like logarithmic singularities or some ramification points, and we ask when there is a pure second order pole, just locally in a neighborhood of the point A. So we suppose that this series converges in some neighborhood of the point A. And what we are going to do is just, this is expansion of U. I was wrong. It's not an expansion of psi. It is expansion of this function U. And we, to solve this equation, we should choose the form of psi such that it is consistent with this form of U. And simple arguments imply that the general form of the psi function with this U is of the following form. It is first order pole with some coefficient alpha, which can depend on T, plus a regular part, expansion in powers of x minus a, some coefficient gamma, plus, not sure that we need the next one, but let us write it nevertheless. And the procedure is to substitute this series into this equation and try to cancel all singularities. This leads to the following system. So there are pools of order 2, of order 1, and also constant term, 0th power. So there are 3 conditions which should be imposed to make the coefficients in front of these poles equal to 0. And in this way, we obtain the following system. A dot is derivative in T. This comes from cancellation of the highest pole, then the simple pole, cancellation of the simple poles lead to the following condition. And finally cancellation of the constant terms lead to the following equation. And they should be satisfied simultaneously. Combining them, so we should differentiate the first equation, apply d over t to this equation, and substitute alpha dot and the beta dot from the second and the third equations. And in this way, we finally obtain a necessary condition of existence solutions of this form. And this condition is a second derivative of a in time plus 4 times u1 is 0. Now, suppose that we have several poles at some points xi. And then the function u for elliptic solutions can be written in this form. From this, we can find, expanding it around each pole, we can find u0 and u1. And the results are as follows. u0 is minus this is near xi. We expand this near some, choose some index I and expand this expression in a series around this point. And u1 is sum over j of derivatives of the Weierstrass function. And a here is now equal to xi. So substituting these expansions into this equation, we get the equation of the following form. Here is our u1. So we obtain p prime xi minus xj. And in this equation equal to 0. This equation is nothing else than equations of motion for elliptic Calogero-Moser system. So this is probably the simplest way to derive this equation of motion from the linear problem. However, this method, using this method, it is not clear how to obtain Lax representation of this equation. This method can be extended to other other kinds of linear equations. For example, for differential difference equation, which is the first linear problem for the total lattice. And again, suppose there is a pole in X at some point, then we expand both functions b and psi around this point, substitute here, cancel all singularities, obtain a similar system of equations, and derive Rusinard-Schneider equations of motion for the poles. Also, we can consider the third order differential equation, which is a linear problem for BKP. And repeating this procedure in this case, we obtain those equations of motion for poles of elliptic solutions for the BKP equation. However, in this case, the calculations are much more difficult, longer and more difficult. Because there are more poles here. Not only the highest pole is of the fourth order. So instead of 3 equations, you get 5 in this case. And also the equation for the toda of type B, which has the following form. A similar procedure allows us to obtain equations of motion for deformed Rusinard-Schneider system. The details of the calculations, you can find them in the lecture notes, which will appear on the site sooner or later. Now we pass to time discretization of many body systems. The idea is as follows. Consider, for example, rational case. Then we represented the psi function in the following form: as a sum over simple poles times some exponential function. Plus t z squared. So this is an expansion of a rational function in simple pole terms. An alternative representation is to find it in the form of a ratio of some polynomial in the numerator divided by a polynomial in the denominator with the roots xi. Substituting this form, before we substituted psi function in the linear equation in this form. But if you substitute it in this alternative form, you get some conditions for y's. You get a system of coupled equations which contain y's and xi's. And from this system, it is possible to show that y's as functions of t satisfy the same equations of motion as xi's. So Kalodger-Moser equations of motion. So the transformation from xi to yi can be regarded as what is called Backlund transformations. Backlund transformation. This is a notion from the theory of integrable systems, and it means that this transformation sends a solution to some equation to another solution. So we know that xi's satisfy Kalodger-Moser, and from this system it's possible to show that y's also satisfy Kalodger-Moser equations. So this is a Backlund transformation. Then the idea is to introduce the discrete time in the following way. Put here index n, and y's, instead of y's, introduce, denote it also as xi's, but in the next step of time. So n is our discrete time. It takes integer values, and the step of time is Backlund transformation. And then you can obtain a system of equations, equations of motion in this discrete time. So let us do this in some details. Consider again this second order equation. And represent the psi function as a ratio of two tau functions. In that example, this tau is a polynomial with roots xi, and this tau tilde is a polynomial with roots yi. Then this equation can be written in the following form in terms of these tau functions. So tau is in elliptic case. We also have exponent in front, and Q is some quadratic expression in x and t times product of sigma functions. And similar ansatz for tau tilde. The same quadratic form plus possible linear terms in exponent. The roots are wise. Substituting all this into this equation, you get move everything to the left-hand side, and the left-hand side, after that substitution, becomes an elliptic function with possible poles at xi and yi. Cancellation of these poles leads to the following system of equations. This term with alpha comes from here. These constants actually can be eliminated by a simple transformation. So we can, without loss of generality, ignore them. From this system, combining these equations, so we should differentiate the first equation with respect to time and substitute derivatives of y from the second equation. And in this way, it is possible to prove that xi's satisfy Calogero-Moser equations of motion. And also y's satisfy the same system of equations. Actually, these equations are almost symmetric under the change x to y and vice versa. Only so this transformation and also change of sign of t of the time transforms this system to itself. However, this proof requires rather difficult calculations. It's not easy because you should, to do this, you should prove some rather complicated identity for elliptic functions. Nevertheless, it can be done. Now we can reinterpret this system as evolution in discrete time. So we redenote the variables in this way, and then this system can be written in the following form. We can exclude so from combining these equations, we can obtain equations of motion in discrete time. To do this, we shift n to n minus 1 in the second equation. And subtract them, subtract this from this. In this way, you get the following equation. So this is equation of motion in discrete time for the time discretization of the Calogero-Moser model. Continuum limit of this equation can be taken by writing here instead of 1 some small epsilon, lattice spacing, and tend epsilon to 0. This limit is not quite trivial because it requires some scaling of variables, but as a result you obtain a continuous elliptic Calogero-Moser system. So let me show some details of the continuum limit, because it is not very direct. It requires some set t n times delta, where delta will be initially put equal to 0 in the limit. And instead of xin, write it as xi of t, which will be coordinates of Cauchy-Riemann particles in the continuous model, plus some other small parameter epsilon times n. Eventually, epsilon and delta will be tend to 0. But there will appear some relation between them, which we don't know at the moment, but we will see what is it substituting this ansatz into the equation. So we can represent n xi of n plus minus 1 in the following form. Xi plus minus epsilon plus minus delta xi dot, and also the next term in the Taylor expansion plus something which has higher order in epsilon and delta. In fact, for compatibility of this substitution, for existence of the limit, we need to require that delta is O of epsilon squared. So substituting this into the equation, we get so we should consider separately here terms with j equal to I, and here we should separate the term with j equal to I, because they require expansion in higher order than other terms. So there I wrote just these two terms with j equal to I. One comes from here, another comes from here. And the rest is proportional to epsilon squared and has the following form. So we need to, you see that the highest singularity in epsilon cancels. This is 1 over epsilon, and this is also 1 over epsilon. Here sign minus, so they cancel. But we need to expand them further to the higher orders in epsilon and delta. And from from this expansion you get something like epsilon squared times xi double dot. So epsilon squared cancels, and we get something which is equation of motion for elliptic, continuous elliptic Calogero-Moser system. Now let us try to do a similar derivation for Rusinard-Schneider model. So the question is, what is Rusinard-Schneider model in discrete time? To answer, we should address the linear problem. Where, if we again substitute here psi as a ratio of two tau functions, we get from this the following equation. For elliptic solutions, it is product of sigma functions. This is tau tilde has a similar form with other roots, which we denote by yi. And substituting this into this equation, we get the following relation. Again, we should cancel the singularities, which are first order poles at x equal to xi minus eta. One pole at this point comes from here and another from here. And also at the points yi, then the pole comes from this zeta function, and it is also here. This leads to the following system of equations. Similarly to what happened for Calogero-Moser system, it is possible to prove that from these equations it follows that xi and yi satisfy equations of motion for Rosenard-Schneider system. So the transformation from xi to yi is a Backlund transformation. In this case, the proof is also not simple. It requires using of rather complicated identities for elliptic functions. I will not show any details on this calculation. You can find it in lecture notes. And again, we can denote xi as xan and yi as xi n plus 1. So introduce the discrete time in this way. And rewrite this in this new notation. Now shift n to n minus 1 in the second equation and divide them. In this way, you get the following system. The continuum limit leads to elliptic Rusinard-Schneider equations of motion. This system was obtained first in 1996 by Ragniska, Nichkov, and Kuznetsov. It is a rather remarkable system, and I should make the following remarks about it. The form of this system coincides with Bethe-Ansatz equations. Which are related to a very different topic, to quantum integrable systems. For example, quantum spin chains related to JLN case. So this is generalized spin chains, and they are solved by the procedure which is known nested Bethe-Ansatz. In the quantum model, the answer is obtained in the form of Bethe-Ansatz equations for some auxiliary parameters which are called beta roots. And then the observables of the system can be obtained by substituting solutions of beta equations to some explicit formulas for some physical quantities related to the quantum spin chain. And in this interpretation, these xi's are beta roots at level n. different n. Beta roots at level n of the nested beta ansatz. However, there are two important differences between beta ansatz equations that appear in quantum spin chains and these equations. The first difference is that here, in the Rosenau-Schneider model, the index n usually take any integer value from minus infinity to infinity. So this is an infinite chain. However, in beta ansatz equations, n takes only finite number of values, 1, 2, n. The second difference is probably even more important because here the number of xi's is the same at each step of time. It is excuse me, this n is not this, let me call it n. At each step of time, the number of roots is equal to n. But in beta ansatz, the number of beta roots is different at each level. The number of roots are m, which depends on n, and there are some restrictions to these numbers, which I will not explain here. However, it is there are some inequalities like this. And this is very important property of beta ansatz equations, that the number of roots is different at each level. So to explain this coincidence in some way is a problem for future. At the moment, it is not clear whether this coincidence of this discrete time Rosenau-Schneider equations of motion and beta ansatz equation are there any serious conceptual reasons for this coincidence? It's not clear. In my opinion, this is a very interesting question to think about it further. The systems, many body systems in discrete time also have Lax representations. But now the form of the Lax equations is different because the time is discrete, so it is not differential but a difference equation, the Lax equation. So let me show you the discrete Lax representation for the discrete time Rosenau-Schneider model. The Lax matrix at the time n can be written as follows. And the second matrix of the Lax pair M has a similar form. Where these functions are as follows. And a similar equation for function g. No. I will not write it explicitly. It has a similar form with some shifts and change of signs here. The discrete Lax equation has the following form. As in the continuous case, it means that the evolution in discrete time is an isospectral transformation of the Lax matrix. So it is clear from this equation that it is a similarity transformation of the Lax matrix. So this is isospectral. And at last, let me show you time discretization of the deformed Rosenat-Schneider system, which can be obtained in a similar way, using the same idea. So you take linear problem for bit order represent psi function as a function of ratio of two tau functions, write the equation for psi through tau tilde and tau, make an ansatz that each of them is a product of sigma functions with some roots y's here and x's here, and obtain, by cancellation of poles, obtain a system of equations for y's and x. Again, the transformation from x's to y's is a Backlund transformation, which sends solutions to solutions. And denoting this as xi at time n, y as axis. Next, step of time, you get a system of equations. However, it has a more complicated form. And as a result, combining these equations, you can obtain equations of motion which connects xi at the previous step of time, xin and xi n plus 1. And this system now has the following form. Mu is some parameter which is related to the lattice spacing of the time lattice. In the Rusinard-Schneider model, it cancels, does not enter the equation explicitly, but here it appears explicitly. If we put this equal to 0, we get nothing else than equations of motion of the Rusinard-Schneider system in discrete time, which I showed you previously. As you take ratio of these terms and get it in the form which was written here before. But now the right-hand side is not 0, and has a similar form like the left-hand side. Namely, it is like this. So this is rather remarkable system, and it needs some interpretation. Its relation to quantum integrable system, like beta solved by beta ansatz, if any, not clear. So this requires some understanding. Few words about continuum limits. In fact, several different continuum limits from these systems, from this system, are possible. One of them, for one of them, introduce another variables, coordinates of particles, which are related to xi small in this way. And rewrite this system in terms of x capital, and then perform continuum limit, assuming that xj n plus 1 is xj plus minus epsilon xj dot plus 1/2 epsilon quadrat x epsilon squared xj 2 dots plus higher terms. And substitute to that system and tend epsilon to 0. For consistency of this procedure, we should require that mu to the minus 1 is of order epsilon. And this is a problem for you to show that this limit gives equations of motion of the deformed Rosenard-Schneider system. Another possibility is to not to make this shift and assume that xi themselves, small xi, can be expanded in this way for small epsilon. In this case, for general mu, for general values of mu, you get just the standard Rosenard-Schneider system in the limit. However, if mu to the minus 2 degree minus 1 is of order epsilon, in, say mu to the minus 2 is 1 plus some alpha times epsilon plus higher terms. Then the limit, the continuum limit is very different because in this case, in general case, you should expand both sides in up to order epsilon. But in this case, this special case, in order epsilon you get identity. So you should expand further up to epsilon squared terms. And this gives a very different and very complicated system of equations of motion, which even is not resolved with respect to xi double dot. the familiar Newtonian form is that it is some function of xi dot and xi. But that system, which is obtained in this special case, is has a more general and more complicated form. So the x double dot enters in some non-trivial way, and this equation cannot be resolved with respect to xi double dot. It's represented in this form. At least in elliptic case, it cannot be resolved. But however, in rational case, when we just erase sigma functions and obtain a polynomial equation, then in this rational case, in fact, this equation can be resolved with respect to double derivatives. Okay. The spin systems of Kalogero-Moser and Rosinar-Schneider type also can be discretized in time. This is rather complicated, but direct procedure using the same ideas as we observed here. So in the next lecture, we will consider field generalizations of Kalogero-Moser and Rosinar-Schneider systems, when coordinates of particles xi depend not only on the time variable t, but in addition to some extra variable x, which is called space variable. So this is rather field theory for two-dimensional, for n fields in two-dimensional space, space and time. Okay, so this will be on the next lecture. And this is all for today.